Representing functions as power series. This video deals with representing certain functions as power series. You will learn how to represent certain types of functions as sums of power series by manipulating geometric series or by differentiating or integrating such a series. Thanks in advance for watching this video. If you like this video, do not forget to like, subscribe to the channel and activate the bell. It is very important for the continuity of this channel. To start, we will see how to represent functions using an infinite geometric series. The first technique for obtaining the power series of a function is to relate the function to the sum of a convergent geometric series. Recall that the geometric series converges if and only if the absolute value of the common ratio is less than 1. Now, if we replace a with 1 and r with x, this becomes, and we can express this as a function. Now you will learn how to represent functions with power series where the function can be related back to a geometric series. Find a power series representation for the function f of x stating the interval of convergence. We rewrite f of x to fit the form of an infinite geometric series. We can do this by replacing x with minus x. So we obtain a power series representation for the function f of x as long as the absolute value of minus x is less than 1. The domain or interval of convergence is given by solving this inequality. To solve item B, we rewrite f of x to fit the form of an infinite geometric series. We can do this by rewriting the denominator as follows. We replace x by minus 1 times 1 minus x in the equation above. So we obtain a power series representation for the function f of x as long as the absolute value of x minus 1 is less than 1. The domain or interval of convergence is given by solving this inequality. To solve item C, basically, we do the same. We rewrite f of x to fit the form of an infinite geometric series. We can do this by replacing x with 3 times x. So we obtain a power series representation for the function f of x as long as the absolute value of 3 times x is less than 1. The domain or interval of convergence is given by solving this inequality. To solve item D, basically, we do the same again. We rewrite f of x to fit the form of an infinite geometric series. But this function does not look like a geometric series. However, with a little algebraic manipulation, we can relate f of x to a geometric series. We need the number in the denominator to be 1 minus x. So we rewrite the function by factoring 5 from the denominator. So we obtain a power series representation for the function f of x as long as the absolute value of x divided by 5 is less than 1. The domain or interval of convergence is given by solving this inequality. So far, we have seen how to represent functions using an infinite geometric series. However, we can use calculus to obtain further results. The ability to differentiate and integrate power series allows us to use known power series representations to find power series representations for other functions. To begin, we state the following theorem. Suppose f of x has a power series representation about center A with a positive radius of convergence r. Then, the derivative of f of x is the term-by-term differentiation of the power series. The integral of f of x is the term-by-term integration of the power series. The radii of convergence of the two power series above are both equal to r. The process of differentiation and integration allows us to create further power series representations of functions differentiating or integrating a known series. Let's see how it works. To start solving this problem, first, notice that g of x is the derivative of f of x. We can differentiate term by term to obtain the series. We use term-by-term differentiation, but since we have got a power series representation for f of x, all that we will need to do is differentiate that power series to get a power series representation for g of x. Since the original power series had a radius of convergence of 1, the derivative, and hence g of x will also have a radius of convergence of 1. Find a power series for the natural logarithm of x. We know that the derivative of ln of x is 1 over x. Hence, the integral of 1 over x is given by the natural logarithm of absolute x, also represented as ln of x. We add a constant c. We can integrate this series to obtain a power series representation for that natural logarithm. By letting x equals 1, we can conclude that c equals 0. Find a power series for the natural logarithm of x plus 1. We know the power series representation for the natural logarithm of x. So all we need to do is replace x with x plus 1, and we get a power series representation for the natural logarithm of x plus 1. Pay attention. Find a power series representation for arctangent of x. Recall that arctangent of x is an antiderivative of 1 over x squared plus 1. We, therefore, need a power series for 1 over x squared plus 1. We start by looking at item A. If we change x by x squared, we obtain a power series for 1 over x squared plus 1. So we find the required series by integrating the power series for 1 over x squared plus 1. If we let x equal 0, and note that the arctangent of 0 is 0, it follows that the constant c equals 0.